Hello, my name is Dan Tempest, and I will be talking to you today about the action potential within a neuron. Um, first thing I would like to talk about is some neuron structure. Okay, so students really need to understand kind of where the stimulus is going to come from. So that would be received by the dendrites. I do like to talk about the cell structure in general, that the nucleus is located in the cell body of a neuron, slightly different shape than a cell that they would normally see in like a textbook. Um, and then an action potential is actually propagated down the axon hillock and then down the axon itself in this direction, um, eventually reaching the synaptic terminals and the axon terminal, and then being sent through a neurotransmitter across the synaptic cleft over a synapse to the postsynaptic cell, which would then send it again. Do like to point out these myelin sheaths, and I like to point out the speed that they impact. So one of the things that we like to show them is that this action potential can actually skip across, called saltatory conduction, over the nodes of Ranvier. And you can see why could probably go faster. So we like to talk about the speed of the action potential being impacted by those nodes of Ranvier. We also will talk about disorders that might impact that and how that would impact the nervous system. Next, I would like to go into ion pumps and how they're going to impact membrane potential and regulate it. Specifically, a couple one of which is called the sodium potassium pump. We'll talk more about that later with repolarization. But essentially, what they do, a really nice job, is getting those ions back to resting potential where they belong, and we'll talk about where those belong when we get into resting potential here in a minute. Across the plasma membrane, each cell has a voltage, and that we call that voltage membrane potential. I like to remind my students that this membrane potential is measured inside the cell, and that'll become important when we show ion movement. The inside of a cell is negative. It's about negative 70 at resting. And the reason why is that we're going to have sodium and a higher extracellular fluid in the cytosol. So we can see sodium in the extracellular fluid out here. So outside of the cell is where sodium is at its highest. And then inside the cell is where potassium is at its highest. So again, we like to talk salty banana, right? Salty for sodium, potassium is high on bananas. So if we're looking top down, outside the cell would be sodium. Inside the cell is that potassium piece. So big bolded part, very important that they understand sodium is higher outside the cell, potassium is higher inside the cell. Then we like to talk about two different types of stimulus. One would be inhibitory, called an IPSP. Um, IPSP would be inhibitory postsynaptic potential. And this is going to cause what we call a hyperpolarization. So we're going to move away from threshold, actually falling below resting, you'll see here. And these are inhibitory because they're essentially stopping an action potential from happening. Opposite of that, then, excitatory, EPSP for excitatory postsynaptic potential. And excitatory because we're moving towards threshold, trying to cause an action potential if the depolarization is strong enough. With an excitatory, we're increasing membrane potential. Okay, so now getting into the action potential itself. Again, we'll start at threshold or at resting potential, about negative 70 on our graph here. Again, measuring inside the cell membrane. So at rest, what I like to show them is this picture right here. It does a nice job at showing, again, that sodium is outside the cell, potassium inside. And then the last thing about resting that we show them is these gates are all shut. So the cell is at rest. A depolarization, moving into step two, a depolarization a stimulus is caused a depolarization of the membrane. And what you'll see here is what that's causing is sodium is coming into the cell. Now, you'll notice that not all the gates are open at this time. These ion channels are not all open. They're only part of it. So that's why we see only a slight rise. It is rising towards threshold. Eventually, if we do reach threshold, we'll have an all or none response in which sodium will rush into the cell, and we'll get into that in step 3. But here we have a depolarization caused by an excitatory stimulus that has caused us to eventually reach threshold. So at number 3 now, we have the rising phase of the action potential happening. So we have a sharp depolarization, huge all or none response, rising phase, and sodium at this time is flooding and rushing into the cell. You'll notice that all of the gated ion channels now for sodium in this area are open. And what I like to do at this time is really just make sense of the graph. Again, we're measuring inside the cell membrane. So what are we seeing here? We're seeing a positive ion enter the cell. So if we have a positive ion enter the cell, it would make sense that if we're measuring inside, that the graph would rise. Okay, so again, just making sense of this. What are you seeing and why are we seeing this rise in the graph? Well, it's because, again, that positive ion with a positive charge is entering the cell. Okay, so eventually the sodium channels will close, and what you're seeing here now in the falling phase is that potassium ion channels have opened. So in an action potential, the first gated ion channels that open are the sodium ones. The second ones that open slightly later, and this is milliseconds we're talking about, but slightly later are those potassium channels. So now we're having a positive ion leave the cell. And that is going to cause, again, what we're seeing in the graph. We're seeing this falling falling phase in number 4, and eventually bottoming out in phase 5. But in this falling phase, again, making sense, positive ion leaving the cell. So if something positive is now leaving, that's what's going to allow us to bring this membrane potential back down. That leads us to step 5. Step 5 is called the undershoot, where it takes a little bit extra time for those potassium gates to actually end up closing. And that's why we actually fall slightly below the resting potential. This is also considered a hyperpolarization of the membrane here. Again, just falling below that resting. Steps 4 and 5 are part of the refractory period. And what I like to talk about with the refractory period as it relates to an action potential is that this refractory period only allows the message to be sent in one direction. So what this picture here is showing you is the blue part is where this action potential is occurring. And the action potential is going to go unidirectionally down the axon. But why does it only go down in one direction? It's because during this refractory period, which is symbolized by this green, this membrane cannot be depolarized again during that time. So because of that, the action potential only propagates in one direction down the axon. Very important concept. All right, so what do I like to do in my class after we've talked about an action potential? We like to do a class simulation. A lot of students are visual, and actual doing the kinesthetic movements of these gated ion channels and the ions themselves in front of them helps them to really ingrain that content. So I've drawn a really simple model here as to what they would be doing at their lab stations. They would draw this right on their tables. You can see a plasma membrane. I would have them do the phospholipid bilayer, but just to save time, I give them this as kind of a model. They're going to have a couple different colored toothpicks. Again, just for the couple different ion channels that we focus on, the sodium and potassium gated ion channels. So the gates are symbolized by these toothpicks. So they're going to have to physically open and close those gates. We use beads, 2 different colored beads, one for sodium, one for potassium, and showing that movement. And they have to do this right in front of me so I can help them if they have any slight misconceptions or mistakes, and we can catch that real time. And I find that students, when they can do this, they really help. It really helps them to understand that content a little bit better. Then for my reference, I used my AP Biology textbook, specifically the nervous system section, and all the information and the pictures in this presentation were from that textbook. Hopefully you enjoyed my presentation on the action potential and some other things that impact an action potential. Take care. Have a great day.